Hello, everyone. This is Rafael Tolentino-Hernandez, and I'm the presenter of this work entitled Thermal Stability of Reduced Graphene Oxide Coatings Deposited in Non-Compact Copper Tungsten Multilayers Produced by Sequential RF Sputtering. Uh, I belong to the Instituto Politecnico Nacional. My co-authors, Enrique Jiménez Melero, Edgar Onofre Bustamante, Francisco Javier Espinosa Faller, and Felipe Javier Briones. They are also from Instituto Politecnico Nacional, from the School of Metallurgy and Materials of the University of Birmingham, and the Escuela de Ingeniería de la Universidad Marista de Mérida. Uh, with population growth and projected future increase, the energy requirements have risen dramatically. Furthermore, uh, we know that the main energy sources are the fossil fuels, which have a very bad impact in the environment due to the global warming, etc. So different energy sources and have been investigated, like renewable and alternative energy. In the renewable sources, we know most of them, like solar energy, biomass, wind, thermal, geothermal from the ocean, and the alternative energy source are commonly the nuclear one. There are two nuclear processes from which we can obtain energy: nuclear fission and nuclear fusion. In nuclear fission, unstable heavy atoms like uranium 235 are bombarded by hot neutrons, which further destabilize the nucleus and fragments into lighter atoms, releasing energy. Nuclear fission reactors are currently used on an industrial scale in many development countries. On the other hand, nuclear fusion starts from the union of two light atoms, usually the isotope of hydrogen, to form heavier atoms and very high energy neutrons. To achieve nuclear fusion reactions requires a very large amount of energy. Uh, Namely, only two forms of induced fusion reactors are currently studied: the inertial confination and magnetical confination. In magnetical confination mode, uh, the reactors used usually are known as tokamaks, and there are toroids formed in the fuel vessel. A point to highlight: to achieve the nuclear reactions from the heavier isotopes of hydrogen like deuterium and tritium, it requires a very large amount of energy. The fuel, the fuel needs to be heated uh, up to 100 million, 150 million Kelvin to induce the reaction. This is achieved by inducing an electromagnetic current by means of coils coupled around the toroid, which also removes the electron from the hydrogen isotope, leaving them with a negative charge, which allows that the fuel to be magnetically confined to the central region of the fuel vessel, away from the wall. This is because there is no material that can withstand the temperature at which the thermonuclear plasma begins to fuse. And that's why the chosen material uh, selected for be the armor in the first wall of the fuel vessels in nuclear fusion reactors are the tungsten, because it's the element with the highest melting point of the periodic table also have a very low sputtering yield and is a hard refractory metal. Um, However, tungsten is inherently brittle. For example, in the figure 4, we can see some micrograph of tungsten ether grade, which was irradiated with was exposed to plasma pulses from 0.3 and 0.9 megajoules per square meter. And we can see in the left side of the micrograph that at the both pulses of plasma, the tungsten fracture uh, from the 0.3 to 0.9. Well, the fracture is more pronounced. But when we have an alloy of tungsten with 5% of tantalum at the same pulses, we can see that the surface are not cracked or fractured. So there are a lot of work on this type of modification of the tungsten material from alloy or another kind of modifications or preparation of different advanced materials for withstand with the harsh environment in a nuclear fusion reactor. Also, we can see that in the micrograph of the left part that the helium can penetrate into the nearly to the surface and can form helium bubbles. Also, the uh, more deep in the microstructure, helium can be formed by transmutation induced by the uh, neutron collided neutron collisions. Recently, investigations on graphene materials have shown that they have the potential to be used as an barrier in the nuclear environments. This is used that the uh, carbon lattice of graphene they have a very geometric, a very tiny geometric form, and these can help to avoid the helium penetration. Also, graphene have a very low sputtering yield and is very flexible and is a very hard material. The very tiny geometric form of graphene lattice uh, uh, make it is impermeable to the most standard gases, including helium. Graphene coatings and membranes have been used have a barrier or chemical barrier to protect metals from corrosion, etc. New kinds of advanced materials are currently on investigation as serve as nuclear plasma components. One of them are the metallic nanomultilayer systems. In this case, metallic nanomultilayer systems from copper and tungsten have been investigated at different individual layer of copper and tungsten with different thickness in the nanometric mode are investigated and have been, um, for example, thermal degradation studies have been performed on these nanosystems to evaluate the operating window in future fusion reactors. In this case, metallic copper and tungsten metallic nanomultilayer have been thermally treated at 4 different temperatures. And we can see that from 750 Celsius, the multi-layer nanostructure starts to degrade, and up to 800 Celsius, we have a type of microstructure like a nanocomposite with a copper matrix and tungsten particles segregated in different regions. In the literature, uh, there is a discrepancy in the mechanical properties reported for these multilayer systems. Multilayer systems with individual layers of varying the thicknesses exhibit different hardness according to different authors. And since there is not a standardization of the fabrication process, there is a high variability in the reported properties, even in systems with the same layer thickness. Um, on the other hand, graphene, graphene have been studied as a radiation barrier to protect tungsten material from irradiation. Tungsten samples were irradiated with helium at 30 kilovolts of acceleration and 900 Celsius. In the micrograph from A to B, we can see that with the increase of fluence of the irradiation of helium, at more fluence, well, the surface is damaged and give at last at the highest fluence to a fuzzy surface. From E to H micrograph, which are tungsten samples coated with graphene obtained by CVD. We can see that even with the increase of the fluence, the surface damage is apparently reduced. Only some spots are seen that apparently more damage. The author report that these spots with more damage in the sample with graphene coating are because are due to the transference of the graphene and the coverture of the surface was not homogeneous. Some spots are with no graphene coatings, and these are the more damaged ones. Also, the loss mass analysis shows that the samples with graphene were lost less mass after the irradiation. The Raman spectra before the irradiation and after the irradiation show no modifications on the G band and D band, and also in the 2D band. And these are attributed that the no damage are presented after the irradiation. Another study where graphene oxide coatings was deposited onto niobium substrates by electrophoretic deposition is presented. They studied the properties of the graphene oxide coatings deposited at different deposition times and how the graphene oxide coatings protect the metal surface against laser of high power, laser irradiation of laser of high power. They find that the graphene coatings apparently protects the metal surface from the laser irradiation. From the Raman analysis, they discovered that exists some kind of reduction of the graphene oxide to a partially reduced graphene oxide. They find an optimal deposition times with the better thermal resistance of the laser. in a deposition time for 10 seconds, and shows that this sample protects even at a energy fluence of the latter of 3.4 per 10 to the 9 megawatts per square meter. This due to the increase in the thermal conduction of the partially reduced graphene oxide, which gives an economically advantage against graphene coatings synthesized by CVD, since electrophoretically deposited graphene oxide coatings can be reduced by some methods like thermally or chemically, and can be homogeneously obtained in all the metal surface, giving the possibility of obtain graphene oxide coatings at industrial scale approximation. This work was divided in three sections. First, the material synthesis. Second, heat treatment. And third, the characterization of the samples. Briefly, we synthesize graphene oxide powders by the modified Humer method. Then the multi-layers that we synthesize was by RF sputtering sequential. We synthesize copper tungsten multi-layers with different thicknesses from 2, 5, 10, 20, and 50 nanometers of individual layers. Then we deposited electrophoretically the graphene oxide onto the multi-layer by in the different samples, and then a thermal treatment was applied in order to reduce the graphene oxide coating onto reduced graphene oxide, and then all the samples were characterized by AFM, nanoindentation, high resolution transmission electron microscopy, and by Raman spectroscopy. Raman spectroscopy of the graphene oxide coatings are presented. We have in the upper part the Raman spectra of the graphene oxide powders used for obtaining the graphene oxide coatings. Then in A, B, C, D, E, and F, we can see the Raman spectra in black of the deposited graphene oxide coatings, and in red the graphene oxide, the Raman spectra of the graphene oxide coatings after thermal treatment. We can observe the well-known D and G bands for graphenic materials. We can see that from the powders, very large, very intense D bands. That's why we have a very oxidized graphene material. When we deposit the graphene oxide onto the multi-layer by electrophoretic deposition, we can observe a slight reduction of the D band, and while this has been observed that during deposition the graphene oxide partially reduced. Also, we can see a shift to a higher wave number of the D band, and this is related to the related to a lattice mismatch between the substrates and the graphene layer. After thermal treatment, we can see that the D band almost disappear, and this is related to the reduction of the graphene oxide when release the oxygen group, and possible restoration of the sp2 character of the graphene lattice. But we also can see that the G band, which is related to the graphene skeleton, are distorted the full width and a half maximum is expanded, is increased, and there's a distortion and shift on the gibbon. This is attributed to a fragmentation of the graphene sheets during the thermal treatment, um, which will be discussed later. By the fitting of the G and D band of the graphene coating, we obtain structural parameters like the crystallite size. In the plot, we have the crystallite size for all the samples in the different samples in A without thermal treatment and in B with thermal treatment. And these crystallite size behavior or evolution are compared to the evolution of the full width and half maximum of the G band. According with Cancado and collaborators, the crystallite size always evolves uh, as the same of the full width and half maximum of the G band. In the sample without thermal treatment, we can see that this trend is followed, both for the sample with thermal treatment. The trend is different for both for all the samples. Also, the bar error, the error bar can show us the dispersibility of the data. Crystallite size for samples without thermal treatment and thermal treatment uh, were calculated using the intensity of the G-band, the D-band and the G-band and the area. That's why usually the intensity is used, but Cancado suggests, Cancado and collaborators suggest that the area is better used not only to see the defects and lines, also the punctual defects. Also, with the Raman data, we calculate the strain of all the samples using a baseline, the data of the graphene powders. We can see that the dispersed strain parameters against the G position of the sample shows a positive slope. This is attributed always to polycrystalline graphenic material, uh, which is according to the graphene oxide powders. Labeled in a circle, in the red circle, are the data for the sample with thermal treatment. We can see also that the error bars are very large, which show the dispersion of the data, and we can see that that the thermal treatment samples have not homogeneous properties. From atomic microscopy, we obtain the topography and phase image of graphene oxide coatings. First, we can see in the F part from up to down, both the top to down, the samples of the 2, 5, 10, uh, 20, and 50 nanometer of layer thickness. We can see that the surface evolves according to the time of deposition or the increase of the thickness. And in the phase image, we can see that there are mostly homogeneous. This is for the samples of not thermal, which have no thermal treatment. For the samples with thermal treatment, we can see that there in the surface appears a lot of grains uh, for all the samples, and in the phase image, we can see some differentials in the contrast, and this is related that we have in the surface different materials. This is important because tell us that during the thermal treatment, the copper diffused to the surface and uh, appears like different grains in the surface, and this is why we observe in the Raman spectra this distortion of the given. You will know that the copper is an excellent catalytic material for graphene uh, materials. That is why it's used usually in the CVD process, copper or nickel. But in this case, the differential, the distortion of the G bands will be related to the graphene, which have more degree reduction than the graphene that is on tungsten. That's why observe a very large dispersion in the Raman data. We also can observe the K distribution plot where the black are the K distribution of the coatings with no thermal treatment, and in red with thermal treatment. And we can see that the thermal treated samples present a very large distribution uh, of the samples and the data. Uh, for the nanomechanical behavior of graphene oxide coatings, we obtain the hardness and the reduced elastic modulus. We can see that for the samples with no thermal treatment, uh, the hardness for all the samples were a little bit more higher than the bare substrate. And with a thermal treatment, a slight increase for the samples of 2, 5, and 10 nanometers. Both the error bar shows a large dispersion as we can see also in the AFM data and the Raman data. Both for the 20 and 50 nanometers, the hardness decreased after the thermal treatment. Also, in the reduced elastic modulus, we shown a slight increase in the for the not thermal treatment to the thermal treatment samples, but also the error bars are very large. So we can conclude that the thermal treatment produced a diffusion of the copper to the surface, and this gives us this dispersion, large dispersion in all the data presented. As conclusions, well, copper and tungsten multilayers with a total thickness of 300 nanometers, with copper and tungsten layers with individual nominal thickness of 2, 5, 10, 20, and 50 nanometers were deposited on tungsten substrate by sequential RF sputtering at room temperature using a magnetron power of 100 watts and copper and tungsten magnetron sources. Raman spectroscopy showed a slight reduction in the band due to the electrophoretic deposition, as well as shift of the band to a higher wave number, suggesting the stress inducing during electrophoresis. After heat treatment, the band was almost completely eliminated, indicating the reduction of of graphene oxide to reduce graphene oxide, which is confirmed by the increase in crystal size. Topographic and phase analysis IFN image of the gold coatings on copper tungsten multilayer substrate showed an increase in the grain size after the heat treatment. Furthermore, the phase image suggests that the copper is floating on the surface due to the heat treatment. Surface copper catalyzed the restoration of 92 domains in graphene, but it also fragments the sheets during the sprouting. And stranded crystal of growth mode was the used using AFM the 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 roughness of the sample was calculated. Uh, So this can be related to the differences and the dispersions in the hardness and the reduced elastic modulus obtained by nanoindentation. The simultaneous evolution of the roughness and the hardness was attributed to the size effects of the hardness and the Berkovich indenter. Well, also an inverse Hall-Page effect. Furthermore, to the improvement of the elastic modulus was attributed to the interface effect resulting from copper infiltration and percolation at the amorphous tungsten interface due to the free volume induced by the position conditions. Acknowledgements to the Instituto Politecnico Nacional, to CICATA Altamira, to the Secretaría de Ciencia, Humanidades, Tecnología e Innovación, to the VCCA, a la Universidad Marista de Mérida, the University of Manchester, the University of Birmingham, and in the staff Unidad Saltillo. Thank you for your attention.